Today I'm going to talk about sequential logic and devices. The digital circuits that we discussed so far, all of them have been combinational circuits. If you remember, the output depends on the input immediately. So whatever is in the input at any moment determines the output. They don't have any types of memory. So no matter what was the previous input or the next input, at any moment the input determines the output at the same instant. So we can say in combinational devices, the output depends only and immediately on their input. If I want to summarize this sentence, I can say they don't have memory. So the combinational circuits, they don't have memory. But sequential circuits, however, act as a storage element. They have memory. They can store, retain, and retrieve the information when we need it. So if we have a combinational circuit, a sequential circuit, sequential circuit, we know that this circuit is capable of storing, retrieving, and retaining this information. So let's see how is a block diagram of a general sequential circuit. A block diagram of a sequential circuit is like this. We have a combinational circuit, as a part of sequential circuit. We have inputs, we have outputs. Okay, so far what we see is exactly like a combinational circuit. We have like a bunch of different gates, inputs and outputs. But in order to have a sequential circuit, we need to add another part to this circuit. We add something called memory element. So memory element is connected to this combinational circuit. So the output of the combinational circuit, not all of them, some of the outputs are connected to the input of the memory element, and the output of the memory element is added to the inputs of the combinational circuit and build a sequential circuit. So entire this circuit is a sequential circuit. Sequential circuit. Okay, so we have one important parameter that we should define, and it is called state. Okay, the binary information, stored in the memory element at any given time defines the state of the sequential circuit at that time. So if somebody asks you what is the state of this sequential circuit, the answer is the binary information stored in the memory element. So let me just write down this element, this definition. We can say the binary information stored in memory element at any given time defines the state of the sequential circuit at that time. Okay, so now we know what is the state of each sequential circuit. It is the information stored in this memory element. So before talking about this memory element, let's see how many type of sequential circuits we do have. There are two main types of sequential circuits. So two types of sequential circuits. The first one is called asynchronous sequential circuits. Asynchronous sequential circuit. So in asynchronous sequential circuit, we know that this circuit depends upon the input signals at any instant of time and the order in which the input changes. So this circuit depends on the input signals, and oh, of course, input signals at any instant of time. At any instant of time. And also depends on the order in which the inputs change. Okay, so let me tell you what does it mean. It means that we have this circuit, we have outputs. These outputs depends on the input at any instant time and the order of inputs that we receive. Well, how do we know what is the order? The order of inputs can be stored in the memory element. Okay, so this one is the asynchronous sequential circuit. A new, like the important part of this definition for sequential circuit is this part, at any instant of time. So at any instant of time, by changing the input, the output changes. Okay, depending to the value of the input and the order of the inputs we received at any instant of time. So we don't need to wait like 1 second, 2 seconds to update the output. At any instant of time which the input changes, the output immediately change based on the value of the input and the order of the inputs that we received. But for synchronous sequential circuit, what is a synchronous sequential circuit? So let me write it on here. Synchronous sequential circuit. Okay, so the output can be determined or depends to the value of the inputs or signals of the inputs at discrete instance of time. Okay, and of course the order in which the signals changes. The order in which the signal changes. For the sequential for synchronous signals, instead of saying the order in which the input changes, it's better that to say the the current state of memory element. Okay, so if we look to this definition, we see that the synchronous uh, sequential circuits are based on the value of the inputs at discrete instance of time. How we can synchronize this this memory element? That this synchronization is achieved by a timing device called a clock generator, which provides a clock signal having the form of a periodic train of the clock pulses. Let me show it here. So first, before showing a clock signal, let me write the definition. So we can say synchronization is achieved by a timing device called a clock generator, which provides a clock signal in the form of a periodic train of clock pulses. Okay, so let's assume we have a clock generator here. The clock generator. Of course, this clock generator has an input like called enable. We can turn it on and off. And the output of this clock generator is in this form. If we show a plane with like two axes, one is time, the other one is signal. The clock is a train of pulses. So the clock is a train of pulses, which I'm showing to you now. So you see this is like a periodic train of pulses. So it's the time. Time is 1, 2, 3, 4, 5, 6, 7, 8. So this one is called the clock. So what is the period of the clock? The period of the clock, which we show with T, of course, is the time which takes for one period of the signal. So how long does it take for the signal or for the clock to repeat itself? It's called period, and unit is second. What is the frequency? Of course, there is an important relationship between frequency and period. The frequency is number of repeats per second. So we can say frequency is equal to 1 over t. And the unit for the frequency is hertz. So frequency says that how many times the signal like clocking per second, and the period says that how long does it take for one period of the signal. Okay, so this one is the clock generator. This signal will be connected to the memory element in order to synchronize the outputs of the memory element. Okay, so now that we know what is the difference? What is the difference between synchronous and asynchronous sequential circuits? Let's talk about the elements, the memory elements. The memory elements, we have two main types of memory elements. They're called flip-flop and latch. So first, let's discuss flip-flop. We can show it with FF as an abbreviation for flip-flop. The storage element used in like clock sequential circuits are called flip-flop. So if our circuit is a clock sequential circuit, which is synchronous sequential circuit, we need to use a flip-flop. Okay, and what is a flip-flop? In a very simple sentence, we can say a flip-flop is a binary storage device capable of storing one bit of the information. So it is a memory which is capable to store one bit of memory. Okay, so let me write the definition of flip-flop. The storage element or memory used in clocked sequential circuits are called flip-flop. A flip-flop is a binary storage device capable of storing one bit of information. Okay, so by the way, we should know that uh, the flip-flops operate with signal transitions. It's very important. So let me just write it here. Flip-flops operate with signal transition. Okay, what does it mean? Let me tell you. If we assume we have a flip-flop here, the flip-flop has an input called in, an output called out, and another input called clock. Okay, so at any transition, depending to the type of the flip-flop, we can say transition from low level to high level, or high level to low level. We cannot have both of them at the same time. Depending to the type of the flip-flop, it can be operate with the transition from low level to high level, or it can operate with the transitions from high level to low level. So if we assume we have this clock cycle like this, and this flip-flop we assume operates with the rising edge, rising transitions. So we see these like arrows that I'm showing with green color. So at any of these transitions, out input transfers to the output. Okay, you see? So it's very important. So let me zoom in here to show you more detail. So as the time passes, so this one is a time, the horizontal axis is time. So when we reach to this time, it's called T0. At this transition, which is T0, whatever it's in input moves to the output. Okay? Until the next transition, the output is constant. So it's not going to change. So it's independent of the input from first transition to the second transition. At the second transition, which I'm showing with T1, the value of the input again moves to the output. So again the output will be constant regardless of the input until the next transition. Again in the next transition, whatever is in the input moves to the output. So now we know the meaning of the definition of flip-flop of the synchronous circuits, that it says that it depends to the value of the input at the discrete instant of time. Okay, discrete instance of time. So what does it mean? It means that this t0, t1, t2, not at any distance of time. Okay, so it depends to the value of the input at discrete instance of time. So we should look to the we should look for the transitions, and at the exactly at the transitions, check the input. Whatever is in the input moves to the output. Stop, output not changing, absolutely no change to the output until the next transition. In the next transition, again check the input. Whatever is in the input, move it to the output. Stop until the next transition. Okay, so it depends to the value of the input at discrete time of instance of time. Okay, so this one is flip-flop. So as I said, it can be we have two type of flip-flops. Some of them are mm, a rising edge, the rising edge triggered, and some of them are falling edge triggered. It means that rising edge triggered means transition from low to high, as I showed in this example. You see, we we are waiting for the transition from low to high, from like low signal to high signal. So we call this type of flip-flops rising edge triggered, or like rising edge sensitive flip-flops. The other type of flip-flops that are falling edge sensitive or falling edge triggered flip-flop, we look for the transition from high to low in order to change the output. Okay, so this one is the definition of flip-flop. The next memory element which we want to learn is called the latch. Latch is also a storage element like flip-flop. Stores 1 bit. But the difference between latch and flip-flop is that the flip-flop is signal transition sensitive, but the latch is like level sensitive. Okay, so let me show you. If we have a latch here and we have output and input, and let's assume we have a clock. The clock is like this. If you remember, I said that for flip-flop we have these transitions at we have the data transfer from input to the output at level transition. But here for the latch, as long as for the clock is high, depending to the type of the latch. As long as the clock level is high, whatever is in the input moves to the output. So input moves to the output. Okay? But as long as the level of the signal is low, output is constant. No changing in the output. Okay, so this type of latch is called like positive level sensitive because it transfers the inputs to the output at positive levels. So we call it positive level sensitive latch. Of course, we can have negative level sensitive latch. Let me show you. So if we assume this one is a clock cycle, as long as the value of the signal is low, as long as you see the value of the signal is low, input moves to the output. As long as the value of the signal is high, okay, no change. Okay, so one thing that I should mention, let's go back to the flip-flops. If we go back to the flip-flops, we see that for the flip-flop, I said that at the transition, we look for this input value. So let me fix it. Okay, okay. At the transition, we check the value of the input. What is the value of the input? We transfer that value to the output, and the output is not changing until the next transition. But in latch, we have a different story. In the latch, as long as the latch is active, for example, for this latch which is positive level sensitive, as long as the clock or the level is active, any changes in the input will be transferred to the output. So if the input changes 10 times during this time, the output will be changed 10 times because the clock is active, the level is active. So like based on the being the active, the input changes transfers to the output. So if the input changes several times during this activation period, the output will be changed several times. But of course, during the deactivation period, the output is not gonna change, it's constant. So the last value of the input, in the active level, which is right before the transition, it is exactly here. Let me zoom in and show you. If we assume, uh, so I said that during this time from here to here, any changes in the input will be transferred to the output. Let's say we have one change here, one change here, one change here, one change here, and one change here. Okay, so change number 1, 2, 3, 4, 5. 5 changes. So during this time, which we call it T0, during this time, the output will be changed from 1 to 2, from 2 to 3, from 3 to 4, and from 4 to 5. And after 5, the clock signal will be deactivated. So the last input right before the transition, will be remain on the output until the next activation level. So if we assume the value of the input, for example, it's 0, 1, 1, 1, 0, the last bit of the information of this 5 information is 0. So this 0 will be stay like a constant on the output until the next activation period. At the next activation period, we look for the inputs. If the input like has any change, that change will be reflected in the output. Okay, so as I explained, flip-flop is edge sensitive, latch is level sensitive. So these two types of storage elements are related, okay, because latches are basic circuits from which all the flip-flop constructed. It's very interesting. So in order to construct any flip-flop, first we need to construct the latch and then convert it to the flip-flop. So latch is the basic construction of any flip-flop. Let me just write it here so you can take notes. We can say the the two type of storage elements are related because latches are the basic circuits from which all flip-flops are constructed. So also we can use latches to store information for asynchronous circuits. They are not practical for for use as a storage element in synchronous circuits, because in synchronous circuits we need to have the synchronized outputs. So we need have a clock cycle which is update the output at any discrete instance of time. So latches can be used for asynchronous circuits, and flip-flops can be used for uh, latches can be used to construct asynchronous circuits. Flip-flops can be used to construct uh, synchronous sequential circuits. Okay. Okay, the first latch that we want to learn today is called SR latch. SR latch. SR stands for set reset. Okay, here is a circuit for SR latch. The SR latch is constructed from two NOR gate. So this one is a SR latch. Input R, which we call it preset input, and input S, which we call it set input. We have two outputs. One of them is called Q, the other one Q bar. The output of one NOR gate is connected to the input of the second NOR gate, and the output of the second NOR gate is connected to the input of the first NOR gate. Okay, this one is the basic structure of any storage element. Okay, let's see how does it work. It's very important to analyze this circuit to see how does it work and how it's able to store data. Let's have a table. If you remember, for combinational circuit we have something called truth table, but the same table in sequential circuit we call it characteristic gate table. So here we have characteristic gate table of SR latch. Characteristic table. Okay, we have two inputs S and R, and we have two outputs Q and Q bar. Let's change the inputs in some orders and to see how does the output changes. Let's assume set is 1 and reset is 0. What's going on if S is 1, R is 0? If so, and let me give the name for these two NOR gates. So first one is called gate number 1, the second one is called NOR gate number 2. Okay, so S is 1 and R is 0. We don't know the value of other inputs of these two NOR gates, but one of the outputs can be determined immediately. Which output is known immediately based on the truth table of a NOR gate? We know that if any of the inputs is 1, the output is 0. So definitely Q bar is 0. Now that the Q bar is 0, this Q bar moves to the second input of the gate number 1, and both inputs of gate number 1 is 0. Because it's a NOR gate, as long as both inputs are 0, the output is 1. So here we can complete the first row of our characteristic table. So Q is 1, Q bar is 0. And before continuing, if you remember, I said that for the latch and even for flip-flops, we need to know the order of the inputs. Okay, so it matters because it has the memory. Because it has memory, the value of the output depends to the value of the input and previous values. So we should be careful about writing the characteristic table. The characteristic table, any combination of the inputs depends to the previous input as well. Now let's change SR from 1 0 to 0 0. Okay, and let's see what's going on here. Now we have now at this situation, which S is 1, R is 0, the circuit is stable. The circuit is stable because the output of this gate number 1 is 1. It moves to the second input of gate number 2, which is 1. 1 and 1 gives 0. So output is stable. So now we change S from 1 to 0. Let's see what's going to happen. If S changes from 1 to 0, this input will be changed to 0. Does the output change or no? Of course no, because the other input still is 1. So we won't have any changes in the state of this flip-flop. So still the outputs are 1 and 0. So we can say if after this state, after this combination, we change it to 0 0, the output still is 1 0. Okay, 1 0. The first row we call it set, because by setting S to R, S to 1 and R to 0, Q will be 1 and Q bar will be 0. And the second row, we say both are 0, but after S is 1 and R is 0. After S is 1 and R is 0. By the way, please look to Q and Q bar. There are two outputs and there are complement. There are complements. So when as long as Q is 1, the Q bar should be 0. When Q is 0, Q bar should be 1. Okay, these outputs are supposed to be complement each other because one of them is a variable Q. The second one is the previous value with the bar on top of it. So it is like the complement of that value. Now let's continue. Let's change the inputs from 0, 1, sorry, from 0, 0 to 0, 1. Let's see what's going on here. If R changes from 0 to 1, the first input of gate number 1 will be set to 1. The output of gate number 1 will be set to 0. So this 0 will be moved to the second input of gate number 2, which is 0. And the output of gate number 2 will be equal to 1. This 1 moves to the second input of gate number 1, and the output of the gate number 1 will be 0. So this one is the state of the circuit. So if we set R to 1 and S to 0, the output will be 0, 1. So one thing that I should mention, before let me just write it down here. First it's 0, 1. What I should mention is that changing SR to 0, 1 is not dependent to the previous state. Whatever is the previous state, by changing the inputs to 0 and 1, the output will be 0 and 1. You can just test it. You can just set you can set the different values for the inputs and see, no matter what is the input in the previous stage, by changing the inputs to 0, 1, the output changes to 0 and 1 as well. So here we are in a state reset or preset. Okay, now let's continue. Let me just have this state here because we need it for the next. So if S is 0, R is 1. If S is 0, R is 1. The output of first gate is 0. The input of second gate is 0. The output of second gate is 1. The second input of first gate is 1. And this one is like this state. And after this state, so because it's dependent, it is independent of the previous state, I remove this arrow. So no matter what is the previous state, by setting SR to 0, 1, the output will be reset. So now what if we change it to 0, 0? So reset is changed to 0. So now one thing, if we consider this circuit as a sequential circuit with no memory, we would say, okay, the input is 0, 0. We already have input 0, 0, so the output should be 1, 0. But it's not the case, because this circuit is not a combinational circuit. If it was a combinational circuit, we could say, okay, yes, because these two combination, we had it before, the output is exactly the same. But no, we know that the output of sequential circuits depends to the previous inputs because they have memory. So we might get the different results. So let's see. So if reset changes from 1 to 0, let's apply those changes and see what we will have. If reset changes from 1 to 0, so here we will have 0. It's 0, 1. Still, the output is 0 and no changes. Okay, so no changes. So the output will be 0, 0, 0, 1. You see, for 1, 0, 0, we had 1, 0. For the other 0, 0, we have 0, 1. Okay, how it's possible? Because it has memory, it has the memory of the previous state. It has memory of the previous state. And based on the value of the previous state, it determines the output of the current state. So let's continue. So we can say after S is 1, S is 0, and R is 1. And finally, the last combination, which is 1, 1. What if the inputs are 1, 1? Again, this situation is independent of the previous situation. So let's just apply these inputs to see what's going on here. If S is 1 and R is 1, the output of first gate is 0, the output of second gate is 0, the inputs of first and second gates are 0, and the output will be 0, 0. So output is 0, 0. Can you tell me what is wrong? We have something wrong here. What is wrong? Of course, I said that the outputs are complement each other. But if we look here, we see that both of them are 0. So it's not possible. We cannot have it because they are supposed to be complement each other. So we say the combination 1, 1 as an input of SR latch is a forbidden condition. So we cannot apply this combination as input in SR latch. So this combination is forbidden. Okay, so now that we reached to this point, let's show this characteristic table in a different way. So the same characteristic table, we can say we have S and R, and we have the Q of t plus 1. What does Q of t plus 1 means? Q of t is the current state. At any time, the value of the output of the signal is called Qt. Qt plus 1 is the next value. It's the next state. So what if we set SR to any value? What is the next output? Okay, so we have 0, 0, 0, 1, 1, 0, 1, 1. If you remember, if S is 0, R is 1, S is 0, R is 1, the output, the Q of t plus 1 is 0, Q2 plus 1 is 0, and we show it with 0. If S is 1 and R is 0, the Qt plus 1 is 1. And now what about 0, 0? If we look to this detailed characteristic table, we see that whatever was a previous value of the output, by setting the inputs to the 0, 0, the output doesn't, the output hasn't changed. Okay, so the previous output remains as the next output. So the same story here. Let me show here. We have this output. We change the input to 0, 0. Q of t plus 1 is same as Q of t. Okay, so we can say if S and R are 0, Q of t plus 1 is equal to Q of t. The Q of t plus 1 is the same thing that was Q of t. And of course, 1 and 1 gives the output of 0, which of course is forbidden. We are not allowed to have this set of inputs. Here we built this SR latch with no gates. We can build the same SR latch with NAND gates, but we need to add two inverters. So let me show you. So if we have two NAND gates like this, SR, Q, Q bar, okay, this is exactly equivalent to this circuit, okay, they are same, but it's constructed with NAND gate instead of NOR gate, and the block diagram or symbol of SR latch is like this. We have input S, we have input R, we have output Q, and we have output Q bar. Okay, now that we learned how does an SR latch work, if you remember in the combinational circuits, we discussed the benefits of having an enable input to activate the signal, activate the gate, or like disable the gate. Okay, so the same thing here. We can have SR latch including enable input, which we call it gated SR latch. Gated SR latch. Let me show you what is gated SR latch. Of course, we all know why we need to have enable input, because it allows us to inactive the device based on its function. An SR latch with a control input is called gated SR latch. Okay, so here is the circuit for gated SR latch. First, I'm showing it. I show it with a NOR gate and then NAND gate. Q and Q bar. So this one is as gated SR latch with constructed with NOR gate, And for NAND gate, we have this circuit. Okay, is Q and Q bar. Both are exactly same. This one is same as this one. And the characteristic table, because now in addition of S and R, we have the third input called enable. Okay, so let's see how is the characteristic table. So let's draw the table. So we have input enable, input S, input R, and of course Q of t plus 1, which as I mentioned is next state of Q. Okay, so no matter what is SR, if enable is 0, if enable is 0, the inputs of both gates are 0, and it acts like a SR latch with 0 0, which means no change. Okay, the previous Q, because the inputs of 0 0. So as long as enable is 0, no matter what is R and S, the inputs of no gates will be 0, and the outputs will be same as the previous output. So we can say if enable is 0, no matter what is X, S and R, I, I, I put X, so we will have Q of T in the output, or no change, no change. If enable is 1, inputs are 0, again the same story, no change. If enable is 1, set is 0, reset is 1, the output is 0, which we call it reset. If enable is 1, the output set is 1 and reset is 0, the output will be 1, we call it set. And if the enable is 1 and the inputs are 1, the output is indeterminate. Okay, so we are not allowed to have S and R 1 at the same time. So indeterminate. Okay, so this one is a characteristic table of gated SR latch. The block diagram of gated SR latch, of course, instead of 2 inputs, we have 3 inputs, including enables, and we have 2 outputs, Q and Q bar. Okay, so now that we reached to this point, what we can do for this like a forbidden state? What if like the inputs both set at 0 at 1 1, so the output is undetermined? So how we can just guarantee, how we can make sure that S and R never equal to 1 at the same time, because I said it's indeterminate. Okay, so how we can how we can make sure that they're not going to equal to 1 at the same time? And the answer is here. We need to build a new type of latch called D-latch. Okay, D-latch. Okay, so D-latch can be gated or non-gated. So I'm going to show you the gated one. So one way to eliminate the undesirable condition of the indeterminate state in SR latch is to ensure that inputs S and R are never equal to 1 at the same time. How we can do that? Let's see the circuit for the latch. So here is the circuit for the latch. I'm showing the circuit with NAND gate. Of course, we can build the same circuit with a NOR gate. So here is two NAND gates. The output of is Q and Q bar. Okay, here is enable input. Okay, so here instead of having two inputs called S and R, we will have a single input. A single input called D, and the input D is connected to this circuit in this form. So D is abbreviation for data. So here is the way we build gated D latch. So if you look to this circuit, we see that the inputs are always complement each other. So it's impossible. Let me just fix it. Okay. Okay, if we look to this circuit, we see that because of this NOT gate, which we have here, always if D is 1, the input of first gate is 1, the input of second gate is 0. If D is 0, the input of the first gate is 0, the input of second gate is 1. So we never going to have the undeterminate state, which is 1 1. Also, of course, I should mention that we are not going to have conditions 0 0 because D is complemented here, but there is no problem with removing the conditions DD. The problem was the condition 1 1, which takes the circuit to undetermined state. So let's see what is the characteristic table of this circuit. So if we show the characteristic table, we have two inputs. One is enable, the other one is T, and the output is of course Q of T plus 1. Okay, so let's look to this circuit. If enable is 0, no matter what is the D, the inputs of these two gates are 0 0, and it is the same no changed, which we removed. So we still have 0 0 by setting enable to 0. So if enable is 0, no matter what is the output, what is the input, the output will be Q of T, which is no change. If enable is 1 and D is 0, the output will be 0, which we call it a reset state. If enable is 1 and D is 1, the output will be 1 and we call it set state. So whenever we want to reset the circuit, we enable it and put the D equal to 0. When we want to set the output, we set enable to 1 and input to 1. If we want to have no change, to keep the information as is, we simply set enable to 0. It's like 0 0. So you see that we don't have the condition 1 1 anymore in this circuit, so we don't have any problem, any problem which results in the output 0 0 in SR latch. And the symbol for D latch is like this. We have two inputs. One is enable, the other one input is called D, and outputs are called Q and Q bar. Okay, so in the next lecture I will talk about the flip-flops.